Dr. Craig Wiegert, thanks for being here today.
Happy to be here.
So you are one of my professors.
Yes.
And we are halfway through Introductory Quantum. We got one semester behind us, one semester ahead of us. And one of the things that struck me in the first semester was this quantum Zeno effect. And you had introduced it as a watched pot never boils, and it's the quantum analog of that.
That's right.
So what's going on? I mean, we know watched pots boil, and what is Zeno of Elia doing in the name here? Like, what's going on here?
Well, so Zeno of Elia was a philosopher and had come up with a series of what he considered paradoxes regarding physics, primarily physics of motion. So one of his paradoxes, for example, is the paradox of the flying arrow, and he says, if you imagine an instant of time when the arrow is mid-flight, clearly that arrow is not moving in that instant because it's just a snapshot of time. And he used that to try to argue that motion, in a sense, was illusory. Okay. So, there are a lot of these paradoxes that Zeno came up with that we don't think of as paradoxes today because we have a more sophisticated understanding of motion. We have the tools of calculus so that we can talk about differentials and limits.
Yeah, that seems like an early infinitesimal.
Right, exactly.
A slice of time where nothing changes in this instant. But if we sum all of those up, we do get motion across time.
Right, right. Another paradox, sometimes phrased as like a race between Achilles and the tortoise.
Yeah.
Right, where you imagine someone who is going to race, let's say, a mile distance, and you look at the distance that they cover as they go halfway, right? So after the first half mile. And you consider that one interval of time. And then you imagine that they cover half the remaining distance, so a quarter mile, and then half the remaining distance, so an eighth of a mile. And you can say, well, okay, if we keep having the distance that remains, then they never actually get to the end in any of those intervals.
Because we can, and you can do this on a calculator too. Like there's no end to dividing by 2. I mean, maybe your calculator will do some sort of floating point rounding thing.
Right.
You can theoretically just kind of always keep going. So.
Exactly. And yet, in calculus or in a sequences and series course, if you've taken that, we talk about that you can sum an infinite series and it could have a well-defined answer. Right. And so the sum of 1/2 plus 1/4 plus 1/8, et cetera, actually works out to be 1.
Right.
So
it will converge to that
right. They converge to that final limit. And so we know that actually the Achilles or the tortoise, they end the race. They actually get to the finish line. But this paradox of having that remaining distance was used as a way of making the argument that they couldn't get to that finish line. So that's where the quantum Zeno effect takes its name from. Obviously, Zeno of Elia didn't know anything about quantum mechanics, but
far-fetched theories. Maybe he did.
Right? Yeah. Well, perhaps so. But the quantum Zeno effect, sort of, the naming of it arose from that, and it really is this idea that a watched pot doesn't boil, which again we know that's sort of it's a saying. It's not really true. It's more of a saying about our perception of time than it is of maybe objective reality, and yet. In the world of quantum mechanics, it can actually occur. And it doesn't have anything to do with our perception of time. It really does have to do with the act of making an observation.
That is fundamental. So we can look at Zeno's paradoxes and go, well, logically we could reason to this conclusion if we assume we can just take snapshots. But we know arrows fly, and we know Achilles will reach the tortoise or will reach the end of the finish line. But what you're saying is that there is some quantum mechanical foundation for some truth to that claim.
Right.
Okay, right. That's weird.
So the quantum Zeno effect is based on something that we call the collapse postulate in quantum mechanics. And it's one of the most controversial aspects of quantum mechanics because it leads to some problems in interpreting quantum mechanics and how it might extend to the classical realm.
This is where we get the differences, the Copenhagen interpretation, the many worlds. Like there's
right.
several competing theories about what to do with this supposed physical reality, but we're just not quite sure which one is actually correct. Is that
right?
accurate?
So in what we call the Copenhagen interpretation, and that's the way in which we often teach quantum mechanics at the undergraduate level, we talk about the act of making a measurement of a quantum system, and that act, if you are making a measurement of a particular quantum quantity, a particular observable, that forces the system into one of the potential outcomes of that measurement. So in our quantum mechanics class, we spend a lot of time talking about spin 1/2 systems or two-state systems, where the quantity that you're measuring, whether it's the z component of spin or whether it's the energy level of the system, really just takes on two values. And when you measure a system, the collapse postulate says, well, if there are only two possible values, the system is going to be found to be in one of those two values. And that's true even if initially the system was not purely in that quantum state. So, we talk about quantum superposition, right? About how a state can be a combination of other pure quantum states. This gets back to the Schrödinger cat idea, right? The cat can be both alive or dead before you open the box, right?
I'll show I forgot to bring. I still have your formula sheet for the final, and you drew cats. I'll show it, but it really made the final experience quite fun. So
great.
Thank you.
I'm glad you like that. So the thing about the collapse postulate then is that no matter how complicated or superposed a system might be, when you make that measurement, you are forcing it into to make a choice. If you want to ascribe some sort of agency, which systems don't really have, but we could say is that the system chooses one of the potential outcomes. Now, if the system was originally in one of the pure quantum states, then we're not going to force it into the other state by making this measurement. We just sort of confirm for ourselves, yes, it was in that state. Right?
Those were the fun problems to do in class, because it was like, oh, well, we're given this state. We know that, and we can proceed knowing that. So those were a lot easier to figure out.
Yeah. So the quantum Zeno effect then has to deal with a system where you might prepare it in one of these known initial states, a pure energy state. But you're also putting it into a situation where you know that after some amount of time, it might have a chance to evolve into a superposition of the first state and some other state, right? So one example of this that we talked about in class was if you have a system with a spin, a charged particle with a spin, and you place it in a magnetic field. Classically, we know that we can cause that spin to change direction. And so quantum mechanically, we can say, well, if we start with a system that is purely spin up and we place it in a magnetic field that might rotate that spin, then after a certain amount of time, there's some probability that it might still be spin up, but it might be measured as spin down if we make a measurement of that spin direction. Right. Another example that might be more familiar to people would be something like radioactive decay, right? We have some unstable atom, a uranium atom or something like that, and it has a half-life. Well, a half-life is really just a quantity that describes the probability that that atom is going to decay in a certain amount of time.
Right. It's for 50% of the material to go through the decay process.
Exactly. So if we had 1 million uranium atoms and we wait a certain amount of time, the half-life of that isotope, then we would expect about half of those atoms will have decayed and the other half will have not. And we can't really predict which ones are going to decay and which ones aren't.
That's all in the quantum fog. We can see what happens from the outside, but maybe still not sure what's going on. Because it's correct that we can't predict which individual atom will do the decaying. Just that half of those million will. Is that...
That's right. That's right. And it's not going to be exactly half, right? It could be slightly more or slightly less than half.
This is what we saw in class where we're doing our measurements of spin. We send 10,000 atoms through to measure spin up, spin down, and we might have gotten like 5,007 and then 4,993. Right. But it wasn't, sometimes it was half and half, but that like fundamental probabilistic nature is definitely there, and we don't really know what's going on.
Exactly. Just like when you roll the dice, you're not always going to come up with, a 6, 1/6 of the time exactly, right? Sometimes more, sometimes less.
Right.
So for something like radioactive decay, again, we could say we start off with an atom that is in some sort of undecayed state, and we know that if we wait long enough, it will probably decay, right? So we've got these systems that we know are going to change with time. And what we want to do is make a measurement of the system to figure out what its new state is, or whether its state has changed, right? So again, in the quantum Zeno effect, as we talked about it in class, we started with a spin system where the spin was in the up direction, and we started rotating it, right? And then we say after some amount of time, we make a measurement. And it turns out that the probability of making an observation that the spin has flipped grows, at least for small amounts of time, it grows quadratically with the time.
Right. That was the T flip. It wasn't quite directly proportional. It had some constants to it, but it was proportional to the number of measurements we made.
Well, so right now I'm just talking about if we make one measurement.
Oh, okay. I see.
So we start with a system that we know is definitely spin up, right? And we put it in a magnetic field that's going to, on average, tend to rotate it. And we wait a certain amount of time, and then we make a measurement, okay? If we wait a small amount of time, so that we know it's smaller than the amount of time it would take to completely rotate around 180 degrees or 360 degrees. But if we just wait a small amount of time, and then we make a measurement of that system again, we know that with high probability, it will still be observed to be spin up. And there's a small probability that, in fact, it will have rotated enough, the superposition will be such that there's a small probability of measuring it to be spin down. But remember, we've got to choose one or the other when we make that measurement.
Right. There's no 30-degree spin. Like when we do that measurement, it either takes up or it takes down.
That's right. Okay. That's right. And that very small probability that after a certain amount of time, we might, in fact, see spin down. For small times, that probability grows quadratically. I see. Right. So let's say that, if we do this measurement after a millisecond, 1% of the time, it will be measured to be spin down. Well, if we waited 2 milliseconds instead before making that measurement, then our probability would be approximately 4%. Okay.
Right.
And that quadratic behavior actually turns out to be really important for the quantum Zeno effect. Okay. So in the quantum Zeno effect, we imagine that rather than doing one measurement after a certain set amount of time, right, we instead do a large number of measurements, total fit in the same amount of time, but we do them more rapidly.
Gotcha.
Okay. And we ask ourselves, well, what is the chance that we're going to measure this spin to have flipped? Right?
For one of those, for any of our measurements as we progressively measure, we're looking for at what measurement in our interval might it have flipped, and then the probabilities of each one of those?
That's right.
Okay.
That's right. And we're really just looking for it happening once, and we'll say, okay, great, it's flipped. Now, if our probability of the flip had grown linearly with time, okay? If, we wait 1 millisecond and it's 1%, then we wait 2 milliseconds and it's 2% or something like that. Then it turns out that if that linear growth, that linear probability growth occurs, then it really doesn't matter whether we do one measurement or whether we do 100 measurements, but closer together. On average, we see about the same probability of a flip. Okay? Because we're making more measurements, but we're also dividing the probability by the same amount.
Right. So you can map it to the linear track of that, and it will still be like you can go 4, you can go 5, and it's still going to have a similar probability each time.
Right.
I see.
Exactly. But with the quadratic behavior, what that means is that at very small times, the probability is really small. And then the probability starts to ramp up faster and faster with larger time. So now if we take this, let's say, 1 millisecond amount of time, and we're doing 100 measurements instead of just one, that means that every time we're measuring the system, only 1/100th of a millisecond has occurred, right? And we also have to remember that every time we make a measurement of the system, it has to collapse into one of the possible outcomes.
We're essentially forcing it to do that.
Right. So after 1/100th of a millisecond, it's pretty unlikely that it will have flipped, right? So it's probably still in the spin up configuration. Well, now it's like we're starting our stopwatch all over again.
Yeah.
Right? So we're starting from our initial system all over again and now waiting another 1/100th of a millisecond before making a measurement, which again is a very small probability, right? And so even though we've made 100 measurements, since our probability has gone down by a factor of 100 squared, we've actually reduced the probability that we'll see the flip.
So is this similar to, I mean, bearing the name, if we take that arrow and we just make our time step really, really small, and then we were to zoom out really large scale, it doesn't look like the arrow's moved at all because we chose such a narrow thing that we've essentially zoomed in so much to the point it's like, yeah, well, it moved, but we chose such a small time step that on the large scale, it's really in the same position.
Right. Okay. Yeah, exactly. And with the quantum Zeno effect, the idea of the collapse postulate saying that we basically reset our system back to its initial state with a very high probability means that we really can, by measuring the system, very, very often, in the limit of infinitely often, but thousands and thousands of times, we can prevent it from flipping when on that time scale it ordinarily would have flipped even with a very high probability.
I see. So and that's the profound result that we derived in class, where we had the probability of that flip occurring was somehow directly proportional to the number of observations we made, meaning the more we observed it, the less likely it was to flip.
That's right.
And in the limit that the number of observations goes to infinity, so would the time it takes to flip. So I have a question. Watch spots do boil. So does this quantum mechanical principle generalize to macroscopic objects, or is this sort of a phenomenon limited to one state? Because our watch pot is made up of, gosh, I don't even know how many states. Every single atom interaction in there would be a state.
Right, exactly. Yeah, it's not something that generalizes really easily to classical systems, even larger than kind of single atom or a few atom systems, and that's really related to the difficulties of interpreting quantum mechanics through our sort of everyday perspective, right? In our classical world, we don't have a lot of experience, a lot of intuition from our lived experience of what quantum systems ought to do,
right?
Because all the systems that we interact with on a daily basis are not individual quantum systems. They are large conglomerations of quantum systems that are not generally in some sort of coherent state with each other, right? And so what we see is this randomized, muddled mess, which is our classical world, rather than these sort of pure states of a quantum system that we like to analyze mathematically in class and that we try to exhibit experimentally, right, by removing all of that complexity.
That certainly made it a bit difficult as an undergraduate, the first time experiencing or doing any quantum mechanics, is that classical intuition is sort of out the window.
That's
and
right.
Your advice at some point was just to shut up and calculate. Like, just trust the math and trust that this makes sense, even though your classical, maybe Newtonian or Lagrangian approach is like sending all the alarm bells that this shouldn't be the result we get, but it is.
Right.
So it seems to me that with the quantum Zeno effect, even with Zeno's paradoxes, they all sort of operate on the assumption that time is continuous, that we can do these infinite divisible steps. I want to ask you, is that assumption well-founded? I mean, the whole field of quantum mechanics is that things are discretized, that there is a lowest possible energy, or that it has to be in one state and not the other, and it's not a continuous spread.
Right.
So is it possible that time itself might not be continuous, and that's why these paradoxes fail so obviously?
So there are some speculations among theorists that time might not be continuous, that we might have to think about quantizing time and space. Um, in high energy particle physics, we often talk about Planck scales, right? So the Planck length and the Planck time. These are all combinations of fundamental physical constants, like the speed of light, like Planck's constant, like the electromagnetic strength, like the gravitational constant, things like that. And these particular combinations of fundamental physical constants, then we can arrange them so that we get something with the dimensions of a length or with dimensions of a time. And so we think of those as being sort of like the fundamental units or the fundamental measuring sticks of space and time. Some people don't really ascribe anything special to those lengths and times, other than to say, well, it's just some sort of natural length scale. It doesn't necessarily mean that at the Planck length or at the Planck time, time or space is discrete.
Right.
What it really talks about is it speaks to perhaps our fundamental misunderstanding or lack of understanding of the laws of physics at those scales.
I see. So just because we have constants like c, g, and h, and we arrange those in certain ways, and it gives us something that's in units of time, doesn't necessarily mean that time itself would follow the number that's output from this combination, being the Planck scale, the Planck time. So it doesn't necessarily mean that it occurs in these discrete steps. It just is a result of our mathematical structure that gave us that.
Well, so I mean, it's not really just pure math, though, right? These constants are constants that are coming from our physical understanding of the universe.
Right.
Right. So when we say that we have a Planck time of a certain very small fraction of a second, we're not necessarily saying that the universe is set up so that its cosmic stopwatch is only ticking in those discrete chunks and there's nothing in between. But what we can say is that because we constructed that time scale from physical constants that came from our current understanding of the universe, if there is something that happens in between at a smaller time scale, our theories don't really do a good job of explaining it. Right? Because our theories are sort of set up to talk about scales that are, the Planck length or the Planck time. And anything bigger than that.
So what could it possibly? I know this is sort of an impossible question because the system's just not set up for it. But what would it look like if time was in fact discrete? I mean, would it give more? Like, would the quantum Zeno effect make more sense at that fundamental level, or would Zeno's paradoxes seem to make more sense?
I've not really thought about in interpreting the quantum Zeno effect through the lens of like a discrete time or discrete space. Kind of theory. You asked what would it look like? There's been a lot of interest from Stephen Wolfram and others on cellular automata and the idea of essentially taking a system with perhaps very simple rules for how it evolves, but evolving it explicitly with discrete time steps.
Okay.
Right. So or like, you think about the game of life. If you know about John Conway's game of life, right? Yeah. So you have this very interesting emergent behavior that occurs in the game of life, but it's happening on a discrete time scale.
Yeah, I never considered that.
Right.
Like it's being forced. There's almost like something moving it from, I mean, it's our computers doing it, but something's forcing it to move from DT step 1 to DT step 2. And is that possibly what gives rise to the emergent phenomena we see in game of life and cellular automata?
It certainly could be, yeah. The game of life is set up explicitly with these discrete time steps, and then with a certain balance of rules that give it this very interesting behavior. Let me give you another example. There's something in population dynamics that we study in nonlinear systems and chaotic systems called the logistic equation. And It describes essentially population growth under constraints. So, you imagine something like a population of rabbits, and you say, well, the rabbits breed really quickly, and if they have access to an infinite amount of resources, well, then their population is going to grow exponentially. Right. But we know that they don't have an infinite set of resources available, and there's probably predators around. So when they reach the limit of their system's carrying capacity, right, when the resources run out or when there's increased predatory pressure, we know that their population can reach some sort of maximum. Now, if you take a very simple model of this that just involves reproduction and then some sort of predation pressure or environmental pressure, resource limits, and you evolve that system with continuous time. So you set it up as a differential equation, and you solve for the population of the system as it evolves continuously through time.
Not as a simulation, because that's not possible.
Well, right. Not as a simulation, but just as a differential equation like we would think of in physics. Right. The motion of a system. What you find is that population starts out small, has a period of exponential growth, and then reaches some sort of plateau. And that sort of S-shaped curve with time is called the logistic curve.
I see.
Okay. And you reach some sort of stable upper limit. Okay, but we know that that's not how rabbits reproduce. They don't reproduce continuously. They go through breeding cycles. And we also know that rabbits are discrete. They're not infinitely subdividable.
Right.
And so perhaps it makes more sense, rather than thinking of this as a system that's continuous in time, to think of it as a system that's discrete in time. So every year we check in on the population of the rabbits, right? Because every year around the same time. And then we just let a year's worth of reproduction and predation happen. And if you do that, then you get potentially very different behavior of the system. You can get the population to, again, grow quickly, but then rather than reaching some sort of stable maximum, it might fluctuate around a couple of different values. Or it might fluctuate around not just 2 values, but 4 values or 8 values. Or it might fluctuate chaotically, sometimes very high, sometimes very low, and in a way that's very hard to predict without knowing sort of the underlying equations that are happening.
So we do see a theoretical equilibrium, but in reality, we know that rabbits don't behave like equations. So we might be able to identify where that theoretical equilibrium should be, but it's not the case that the rabbits are always there. They're going to be bouncing between or above, below that equilibrium.
That's right. And again, both of these are just models, right? Very simplified models of what's really happening. But what's really interesting is that, to your point about discrete time versus continuous time, here we have a system where under continuous time assumption, it has this very well-behaved endpoint. This very sort of fluid growth up to some sort of stationary, steady state behavior, long time behavior that's very easy for us to model and solve. Under the assumption of discrete time, which in some sense might sound easier because I don't have to solve a differential equation anymore.
Right.
All I have to do is just kind of iterate a function a whole bunch of times. But under that very simple change of our system from continuous to discrete time, we end up with wildly different behavior. Sometimes the behavior still is convergent to some sort of steady state, but it doesn't always have to be. It kind of depends on the setup of the system, whether or not we might end up with some fluctuations between 2 different stable populations or a greater number of stable populations, or whether we end up with this chaotic behavior. And it's really just about how we're modeling that system, continuous versus discrete.
So I have a question then, and this might be a bit far-fetched. That seems to me to highlight the difference between classical mechanics and quantum mechanics, where classical mechanics, we sort of treat time as if it's discrete because we're at this super zoomed out level where tiny infinitesimal steps are not noticeable to us. We just get the larger phenomenon of maybe motion. Is it possible that quantum mechanics might be operating on that discrete time system, but at the high level, at the classical abstraction of that, it appears to just be continuous?
Well, It's hard to say that because most of the time that we're studying quantum mechanics and its behavior, we're still operating under a continuous time assumption.
Okay.
Right?
Yeah.
The act of making a measurement can be something that happens discretely, right? So the whole idea of the collapse postulate and the idea of now I'm making a measurement, right?
Sort of has to. I mean,
right.
It has to occur at some time.
Exactly. And so we're dividing time up into sort of a before and after.
Right.
There's our discretization, but it's in the act of making the measurement. In between measurements, we still model that quantum system with continuous time.
I see.
Right? We still have a set of differential equations. The Schrodinger equation is a differential equation in time that talks about how the system evolves. Right? And so even though we don't know for sure what that system is because we are not always observing it and always disturbing it, right? We can predict if we start a system at this initial state and we let it evolve, quantum mechanics, the equations of quantum mechanics tell us what we're likely to see happen later on. And again, even though we can't like peer inside the box as it's happening, we can at least do measurements at different sets of times. We can do repeated measurements, and we know from all the experimental evidence that quantum mechanics, the Schrodinger equation, under that continuous time assumption, actually does extraordinarily well.
I see.
At explaining the universe.
I see.
Whether or not it breaks down at the Planck time scale, we don't know.
Right, because then we have the issue of, well, the thing we're using to probe the system is also subject to the same constraints of the Planck scale.
Right.
So I see. So I just threw a bit of a maybe far out theory at you, and it's my understanding that in your time as in the physics department, as a professor, even as the department head, you've had these come up in email theories.
Yes.
So tell me about that. Are there some that stick out to you? Is it sometimes like just super crazy, no way this would make sense, or do you get some that are like, oh, that could go somewhere?
So all physics professors experience this, where we'll get emails out of the blue, sometimes targeted to individual professors, sometimes it's to an entire department or multiple departments. Sometimes it's regular postal mail. It's not email.
Oh, I see.
And it will be someone who is very excited to tell you about their understanding of the world.
And for clarification, this is not students. These are just people in the public.
That's right. This is the public, folks out in the public. They may not be affiliated with the university in any way. They're probably not alumni of the university. Although sometimes they are, but generally not. They could be affiliated with some other university. They could just be living in the area. They could be casting a wide net. I've gotten emails and letters from people in Georgia, but also from neighboring states. I think I've gotten one from out in Colorado before. So people just trying to get recognized for what they feel is a truly paradigm shifting understanding of the universe. And it's not really. I mean, you look at what it is that they're proposing, and it's pretty clear that they lack a lot of fundamental understanding of introductory level physics or mathematics. Sometimes there's really no math there. And that's always a big danger signal for us as physicists, right? Because mathematics is the language that we use to describe the world. Sometimes there is quite a bit of math, but it's always it's almost always simple proportions, simple quotients and factors. You almost never see differential equations. You almost never see much in the way of calculus. It's really, someone who basically says, well, I've got these, small set of concepts that I know about. And if I combine them, I multiply them together, whatever that might mean, that equals some third or fourth concept. in my mind, and that somehow explains the universe to me.
Right.
And so, on the face of it, the math is very hard to understand. Even though it's simple math, it's very hard to understand what it's trying to say, what it might be trying to predict or explain about the universe. And the theories inevitably construct a very large amount of narrative around these equations. There's really no experimental evidence in any of this, aside from perhaps casual observation or speculation about how a system might operate. But I've never seen one of these where someone has presented data that they've done in some sort of lab setting, or even, casual data taking.
Right.
It's
like
really,
maybe like astronomy data where they do repeated observations of their own. Like, oh, I can see this, I'm going to write it down.
Right, right, exactly. There's really no sort of systematic data collection or data analysis that goes on. I'm
sorry.
Yeah.
I understand that these people that send in these theories, obviously they're maybe not to par, or they can't be considered as serious scientific theories. But how do you feel about the fact that this happens, that there's people out there who are so excited about the physical world that they are so inspired to reach out to scientists such as yourself? Like, is that something you see as a positive?
Qualified positive. Yeah. I mean, I think it's great that people are thinking about the world around them. I've certainly had plenty of wonderful interactions with the public when they learn that you're a scientist, that you study physics, or that you have an interest in astronomy, and they start asking lots of great questions about how the world works, how the universe works. But they do it from a place of, oh, I've always wondered, or I've heard X, Y, Z. Is that really true? Or and sometimes you're able to work with them and notice that perhaps there's some misconceptions, or some sort of alternate conceptions of the world, or just a lack of understanding because they haven't been exposed to the ideas.
They haven't seen the formalism behind
it. They haven't seen the formalism, but they're certainly excited about it. And those conversations can often be very productive and positive, because you can provide them with some of your understanding and expertise, and point them to other resources that they can use to learn more about it. And they're very receptive to that, right? By contrast, these unsolicited emails and letters, usually they come from a perspective of not, I've always wondered, and what do you think of this? But I have discovered something truly new, and it must be true because I'm convinced of it, and now I need to convince the world of it.
So they're sort of married to the ideas they send to you, and there's a lot of confirmation bias going on behind this. Okay.
And often a lot of sort of, tinged with conspiracy-minded aspects. Like, well, no one else is talking about this, and that's just further proof that I'm right because it's a cover-up.
I see.
Or I have to try even harder to get the word out because it is so important and I'm being repressed.
Maybe that's why you got an email from Colorado, because he sent it to all of his surrounding universities, and the radius made it all the way here to Georgia.
Could have been. Going international soon.
Right. So I just asked about if you're excited about people sending you theories, and you mentioned some of the risks of that. Your background is in physics education. I mean, this is sort of your bread and butter. I mean, how do you deal with this in the academic sense, or in the broader population sense? Like, do you have a method for doing that?
So my interest in physics education is not as strongly focused on outreach and public education. Okay. I'm more interested in how physics majors or astrophysics majors understand their physical theories that they're learning in the classroom, or how they apply them. And in particular, for me, I'm very interested in how they make use of mathematical concepts in the physics classroom. But there is quite a bit of work that people do in what we would think of as like public outreach, or sometimes we think of it as informal learning, informal environments for learning.
That's essentially my goal here is to do exactly
right, yeah,
that.
Exactly.
But you don't have to sit through 3 years of calculus. So
yeah, and I think that's a very important aspect of how we learn, that perhaps needs a lot more study and perhaps a greater commitment from universities, because it so often feels like the sorts of outreach that we do is either individual or single department level. It can be very difficult to sustain over the long term.
Yeah.
And doesn't often have a lot of sustained institutional support. Sometimes does. But when we think about how we might have gotten interested in physics or astrophysics, and how other students get interested, how professors got to the careers where they were. When people tell their stories, it's almost always something like, well, I had an inspiring teacher, right? But more often it's, well, I found this great book in the library, or I saw this great public lecture and that got me really excited, or my parents got me the subscription to some sort of science magazine, or I took a field trip and it really sparked my interest.
Me, it was YouTube videos. I mean, that was watching these going, I don't know what any of this means, but I want to know what it means, and now I'm here at university. So
right, yeah, and I think that the rise of the internet and the ready accessibility of things like YouTube has been really important. So people who are watching like 3 Blue 1 Brown or Veritasium, or Wiegert, those have been really inspiring, I think, to the current generation.
Yeah, certainly.
And I think we can always do more with that. There's another aspect to that too. It's not just about inspiring the next generation of students. It's also about making sure that the populace is informed about how we think about the world and what we're doing to study the world systematically.
Yeah, the goal is not for us to be these mysterious scientists like doing something in the basement of the physics building that people have no idea what's going on. It's like we want to be open, like these are the methods and this is what's actually going on here.
Right, exactly. And especially when you think about physics, it might tend to lend itself to people worrying or thinking a little bit more outrageously about what could be happening. So, the example of when the Large Hadron Collider first came online at CERN all these years ago, there were a lot of public protests about it, and people worrying that turning it on would create these, black holes that would end up destroying the
vacuum
world.
Decay.
Right. Exactly. And so there was a lot of effort that needed to be put forward to communicate that, no, we're not destroying the world by turning this thing on. The scales that we're talking about are very, very different here. But there's a germ of truth in some of that. This idea of microscopic or atomic size black holes. Well, that actually comes out of a high energy particle physics theory, that we might be creating these atomic or subatomic black holes that would then very quickly evaporate from Hawking radiation, and certainly would not pose any danger. But it sounds dangerous.
Yeah, it sounds scary. Yeah. And I've sort of experienced that myself as I've grown as an undergraduate. A common thing that I thought before experiencing physics or being exposed to physics is that, the government and militaries have all of these crazy technologies that we can't even fathom. And I'm not saying that's not the case. I'm sure it is. But being exposed to physics, I can sort of have a more rational mindset of, maybe the theories just aren't even there. Like these crazy technologies that I think might exist might not even be physically possible. So a lot of those fears have been alleviated by an understanding of, this is where physics is at, and maybe these crazy technologies that I think might exist just physically can't. And that fear's been alleviated by that understanding.
Right. So, but it took you a while to get there too.
Yes, certainly. Yeah.
Right. You've reached that point after several years of studying undergraduate physics, and before that having a sort of science-oriented high school education. And we think about most people don't have that background, and so You know, I think it's an important question for us to consider. How do we get across the important work that we do, the consequences of the work that we do to the larger public when we're competing for their attention and time.
And funding.
And funding, yeah. Funding both for doing the science, but then also funding for actually communicating that science.
Right,
out to
which
the
is a
public.
little bit ironic.
Yeah.
Like, we need your money so we can tell you what we're doing.
Right.
But I understand. But you mentioned that that's not primarily your focus. You were more internally focused in academia. So when you were inspired to do physics education at some point, was there some sort of goal or something you saw that needed to improve with the research you do?
So I got into physics education through sort of a roundabout way. When I was in graduate school, I was actually studying cosmology. And my dissertation work was on essentially looking at statistical gravitational microlensing of high redshift quasars.
Neat, very neat.
And using that to sort of constrain the amount of compact dark matter there might be. And it was very interesting work. I loved the work that I did. But I also really enjoyed the teaching experiences that I had as a graduate student. First, as a graduate lab TA and discussion section leader, and then I served as a TA for some upper level courses. I also did some tutoring and outreach in the Chicago Public Schools, and those experiences really, I think, informed my my passion for wanting to help people learn physics.
Right.
and learn the math behind physics and get past those mental roadblocks. So when I got to Georgia and was got my current position, which is a sort of more teaching focused faculty position, that really sort of was exactly what I was looking for.
Right.
Was this way to teach students physics at many different levels, but also just really try to understand the challenges that they face in learning physics and try to help them learn that better, but also do some research in understanding what those difficulties are.
So in your experience, has it mostly been mathematics? For physics students, I mean.
I mean, look, I don't want to say that math is the primary problem.
Okay.
Because when you study how students learn physics, how hard it is to learn physics at various levels, there are all sorts of things that come up. There's a lot of conceptual reasoning skills that students have to develop that are very subtle, right?
And probably prerequisite to even the math.
Right. And there's the social aspect of learning physics and the idea of sort of being with a cohort of fellow learners. There's this, the idea that you're not really learning any subject in a vacuum, right? You're learning it with others, not just the instructor. You're learning it based on your previous experiences and trying to incorporate that new knowledge into what you already know. And that's different for every different person, right? So it's not, I don't want to reduce it to just, learning physics is problems with learning math.
Right.
But I do think that it is a challenge, or one of the many challenges that students have is being able to transfer the skills that they've learned in a math course into a physics context.
Right.
It's something that I experienced as an undergrad. I took a bunch of math courses. I minored in math, and I loved the math that I took, but I often felt as I was learning it in the math classroom that, well, this is cool, but why do I want to learn this?
Yeah.
Like, I mean, I want to learn it.
Question.
I want to learn it for the sake of learning it. I want to learn it because I signed up for the course and I want to do a good job. But what should I do with this? Why did someone even come up with this idea? And that was almost never asked or answered in math courses.
Yeah, it's almost not its job. It's
Yeah,
just
right. It may
gives
not
you the
be.
tools.
It may not be. I would love to have a set of math courses that explores not just the math itself, but the thought processes behind it and the historical developments and the motivations for coming up with this particular theorem or this realm of study.
And sorry, that almost creeps into like logic courses where it's mathematical in the sense that we're relating things through. I mean, I can loosely call them equations, but if we take like a modal logic course or a propositional logic course, I mean that's you're wading into philosophical territory there. Instead of just using or being taught the tools, you're saying, okay, well, why these tools?
Right.
What is the motivation behind using this set of equations and not this other one? Like, why did our system arise to be this way and not another way?
Right. Or you can think about, and I don't claim to know much about this, but when you learn, when I took a course in topology, I learned later, well, okay, really that was point set topology. And there are actually other equivalent ways of constructing the field of topology that don't rely on sets of points.
I see. Okay.
That are completely equivalent and may give you some additional insight into the realm of topology. But it's sort of the standard way that it's taught. So yeah, you can think about, well, are there other ways of understanding these same sorts of mathematical abstractions, but maybe not built on the same foundations that you learn them from, built on other foundations. We base a lot of the math that we learn on essentially set theory, right? Does it have to be that way? Probably not. Maybe not. I mean, sets are pretty fundamental, but I'm sure there are other ways of thinking about certain areas of math that don't reach back to the sort of the foundations of set theory.
And who knows what that structure evolved to the point maybe where our current structure would look like.
Right.
There's no telling, really.
Right. So back to my feeling in math courses. I realized that I was a physicist, or that I wanted to be a physicist, when I'd take these math courses and then I would see the math being used in physics, and I'd all of a sudden have that aha moment of like, oh, this is why I studied this, right? It may not have been, right? There are many different reasons to learn linear algebra, for example, or differential equations, but seeing it used in the physics classroom and seeing actual systems that were being modeled successfully by that math was, for me, the real inspiration there. And I think that is where a lot of the difficulties can then creep in understanding, where students might know the formal math, might be quite adept at the mathematical manipulations, at the sort of the skills that they learned in the math classroom, but might have a really hard time making that transfer of those skills into a physics context.
Because you're sort of shifting from a skill of process to a skill of application. I mean, I certainly experienced this going through Calculus 3, vector calculus. I blanked on the name there.
Yeah.
But when I was learning vector calculus, this idea of like flux and flux integrals and surface integrals, the way it was taught to me, I was essentially memorizing a process. And it's like, okay, I'm going to set up the integral in this fashion, and then I'm going to do these steps to do the integration. But it wasn't until I took electricity and magnetism with Dr. Lewis, where he had sort of re-explained all those surface integrals. I'm like, okay, I understand why I'm using this tool to accomplish this goal. I'm not just memorizing a set of steps that I would have done in Calculus 3. So is it that sort of gap that can be difficult to jump to go for the physics student to say, okay, I have my tools and I have this great toolkit of calculus or differential equations, but what is my motivation for applying this tool in this scenario? Like, is that what you would characterize as the physicist mindset?
Yeah, I mean, there's several difficulties, right? It could be, I have this great toolbox. Which tool do I use? The toolbox analogy, I think, is great because it can be the situation where a student says, okay, I've got all these tools, these mathematical tools, which one should I use? It may be the case of, do I even know whether or not I have the tool in my toolbox? Recognizing that it's there can be the struggle. for some students that, yes, you have studied this, and you can apply it. But then even like, okay, great, I've identified which tool is the most appropriate, but maybe I've never used the tool in quite this way before, or for this particular application. So, is the way I used to use the tool still going to be applicable, or do I need to learn something a little bit more sophisticated, right? So those can all be aspects of the math difficulty in physics.
I see. So I'll ask, in your time in academia, have you seen a shift in physics education, or like what does the current of that look like from when you first came into academia as a physics education researcher until now?
I think that there's definitely a wider understanding among not just the physics education community, because this is something that has been talked about for decades.
Right.
But I think there's a better understanding among physicists as a whole, that mathematical understanding, the idea of transfer is something important.
Right.
That it's not something that we can just assume that, because it was easy for us in some context, it's going to be something that students will have equal amount of facility with.
Yeah. And certainly top theoretical physicists are also world-class mathematicians. Like that is sort of the primary tool that's needed.
Right. I will say, one of the things I enjoy the most about teaching at any level is when I am able to see how a student is thinking about solving a particular problem or thinking through some sort of conceptual difficulty, and their process of thinking about it, whether it's the math usage or the conceptual reasoning, is different from the way I would have done it. And not worse, sometimes better, actually, than the way I would think about doing it. And it's just always amazing to me because it just opens up this new pathway of thinking. Right. And it has happened every single year that I've taught.
That's awesome. There's always been a student who you've been like, whoa, that's
always weird. Been situations, multiple situations where I have learned a different way of thinking about a particular problem-solving process. And it can be something as simple as kinematics, or as simple as lens diagrams, and it could be something as complicated as quantum mechanics. But always there's something there, some insight that a student gives me that I didn't have. Right. That then, if I have the time, I can sort of reflect on that, and it can help sort of deepen my own understanding of the physics or the math behind it. That's been a lot of fun.
See. So I'd like to switch to a bit more of a philosophical set of questions.
Sure.
So we've just sort of laid out your personal pedagogy, like the methods you use for teaching and the reason why you got into it. But what is your thoughts on epistemology? What does it mean to know something? Because it's not a trivial question. In physics, we sort of assume the triviality of that question. Be like, oh, well, we know this thing happens because maybe we can see it, or maybe we can predict it. But at a really fundamental level, what do you think it means to know something?
Oh, wow.
Yeah, easy question. Right?
Yeah. Throw me the real curveballs here. I don't know that I have a well-formed philosophy of this. I sort of muddle along like everyone else. I've certainly had some conversations about this with colleagues. I guess I sort of hail from perhaps an old school, positivist view or rationalist view of the world. I feel like our best way of understanding the world and knowing the world is through doing experiments, through following a logical thought process as much as we can. When I say doing experiments, I don't just mean in the lab, but I mean any sort of repeated systematic observation that is not necessarily purely individual, that needs to be checked against other people's observations, other people's understanding of the world. I would like to think, I think I grew up thinking that it would be possible for one to sort of understand objective reality purely on their own. I don't think that's the case.
I think that's the pure experimentalist mindset. Where
Yeah,
I don't know if it's true until I can myself prove it through experiment.
right. I definitely I don't ascribe to that, right? Otherwise, it would be a very limited set of knowledge I have of the world. I do have to, trust in the expertise of people in other domains, that they've done that work, and I can hopefully understand and trust their results. But I've definitely grown into this understanding that what we think of as knowledge is very social. It's very socially constructed, but it does have to be based on some sort of shared reality. And I do believe that that is a foundation of what we mean to know something, right? It's not just that you know something that has happened to you. That may be all well and good, but in order for it to be, I think, useful or generalizable, it's got to be something that other people have also experienced, that you can come to some sort of understanding and agreement on. Honestly, you could imagine that it's kind of wonderful that the universe works that way.
Yeah.
Right.
Yeah.
There's nothing, I guess, that says that the universe has to be orderly. You could imagine situations, like multiverse movies, in the Marvel universe, multiverses where the laws of physics change every day of the week or something like that, or they're different in different locations in space.
Yeah.
And the fact that it doesn't seem to be that way, that we do seem to have a reality that we can mostly agree on and test independently, and look for that agreement, is kind of wonderful, right? Because it means that science is possible, right? That sort of understanding of the world is possible.
So you're getting at that repeatability aspect. Repeatability. Yeah, I said that right. Where it might be the case that I observe something or that I create something in a lab, but if I go, oh guys, come look what I made, and then I can't replicate that, or I can't give you the set of instructions for you to replicate that, then that's sort of, well, we can't say we know this to be the case because, well, we can't confirm it like from the exterior or somebody else doing the experiment.
Right.
So I want to ask, the definition you just gave, it's my sense that that's your sort of broader worldview as well. So is your worldview inspired from science, or do you have a philosophical mindset that inspires your scientific endeavor?
I think it really comes from the science. I don't think that I developed that before getting into math and science. In fact, I probably, when I look back at my upbringing and I look back at the sorts of things I thought about as a kid, I definitely wanted there to be a lot of sort of magic and unpredictability in the world. We didn't have Harry Potter when I was a kid, but we had something similar. We had fantasy novels and magical things, and I really got into to that sort of fantasy understanding.
Were you a Doctor Who fan by any chance?
I was not. I had a lot of friends who were, though.
Yeah.
But I was a big fan of Tolkien and C.S. Lewis. I was a big fan of stories about witches and wizards, pre Harry Potter, and I don't know what it was about it. Just the fact that made the world more interesting than my lived experience or something like that.
Right.
So I definitely was perhaps predisposed to thinking more magically or mystically about the world. And I think the process of studying physics and math and other sciences in high school and college sort of matured my understanding to this idea of repeatability and sort of a shared, rational, objective view of the world.
I see.
It can be kind of frustrating, right? I mean, we all have individual lived experiences. We all have situations where something has happened to us, and it may be something that we cannot explain immediately, or we might not have any good explanations for it. And maybe there is a perfectly good explanation, but we just don't know about it.
Right.
And then we tell someone about this, weird, bizarre thing that happened to us, and it's hard for them to understand what happened because they didn't experience it. But in their own world, they had something bizarre, interesting that happened to them that was unexplainable. So we all have these individual experiences, and yet, they don't amount to much other than your own experience
as being a personal experience.
Yeah, being a personal experience. If they can't be replicated, if they can't be shared or analyzed, I mean, they're still there, but I don't know that I would think of them as part of knowledge.
Right.
Yeah.
Right. Because of that repeatability aspect, because of the way we've chosen to define that. You do take on that scientific mindset, or I sort of broadly characterize that as the scientific method, and a very sort of Socratic way of going, okay, this is the theory, and then we're going to question it, and then we're going to iterate on it, and then see if it's repeatable.
I do want to I want to say something about that, though.
Sure.
We have to be a little bit careful about what we think of as the scientific method.
Okay.
Because I think when we talk about the scientific method, a lot of people's understanding of that is perhaps based on a middle school or high school science fair experience, or this is the unit where we talk about the scientific method, and it's presented as something that is very orderly. And what we have to remind ourselves is that is that's a story. That is a very simplified model of what actually happens when science is being done. If you look at people who have studied the scientific method, the scientific processes that really occur in day-to-day life in labs, they come up with these crazy diagrams, wonderfully complex diagrams for flow charting what really goes on,
like where the thought process takes you every time.
Yeah, and so this idea is you've got these, this hypothesis, and then you've got data collection, and then you've got analysis of your data, and then you have some sort of conclusion, and that you've got this strict linear process that then terminates. Is really not at all how science is done. And in many ways, trying to impose that sort of artificially on a middle school classroom for a science fair or something, I think is doing students a disservice.
I see, yeah.
Because it short circuits the natural creativity and questioning nature that we know students have, that kids have. That we'd like to maintain as adults, as scientists. Nowhere in that description do we even talk about, well, where did that hypothesis come from in the first place? There's usually some sort of period of informal observation. I always wondered why, blah, blah, blah. Or I seem to notice something happening. Let me investigate further.
Right. So we've sort of quashed that natural inquiry with this strict formalism that you learned so early, middle school and high school.
Right, exactly. In fact, when you think about doing the scientific method unit in these science classrooms, and this first step of you got to come up with a hypothesis, sometimes students flail. They really struggle because it's like, well, what should I do?
Yeah.
And it's often very artificially constructed because it's not based on their own natural curiosity or observations that they've made about the world sort of informally. So now you have this hypothesis, right? Now you start collecting data. Well, it's almost never the case that you have constructed your experiment in such a way that you're just getting perfect awesome data.
Right. I mean, from the get-go, there's confirmation bias because you have a hypothesis.
There's that, and there are inevitable difficulties, right? You're collecting the wrong data. You're not collecting enough data. Your equipment's breaking down. You're collecting data that is for a completely different question. So, okay, maybe we go back and modify that hypothesis, right? Maybe we realize that the hypothesis is completely ridiculous, right? That the premise is fundamentally flawed, and we need to start over. Sometimes during the data analysis process, you realize I gotta take more data. I've gotta modify my hypothesis. I've gotta add to the hypothesis. I've gotta go back and collect some more data and before I do more analysis. And even when you get to the stage of drawing conclusions from that, that's not an endpoint. That's then saying I've got some sort of systematic way of understanding this this data. It's addressing my hypothesis in some way. What's next now? That's just going to suggest the next question.
And you're still open to interpretation at that point.
Right.
And we even see that at the highest, I mean, even at the complex quantum level, it's like, yes, we've followed some sort of process, or we've noticed something about nature that allows us to inquire further. And maybe we've used our formalism, our toolkit to arrive at some conclusion, but it doesn't stop there. Like there's still big disagreement about how we are supposed to actually go and then interpret those results.
Right. Right, exactly.
So the reason I ask about the epistemology is because I'm sort of wondering, is there still room left for that sort of mysticism, or that has the scientific method, or not the scientific method, but the scientific model extinguished all of that? Because quantum mechanics seems to be like, for some people, like almost a glimmer of hope in the non-deterministic realm. Like, do you see that existing? Like, does quantum mechanics provide some room for that mysticism to still be alive?
For some people, perhaps so. I don't necessarily think of quantum mechanics as being particularly mystical. It's definitely hard to understand and counterintuitive in many ways. And I think that for many people it might seem mystical, but it's a very well established theory of the world. It's a very experimentally successful theory, and so I think that we can't rely on something like quantum mechanics to say that somehow leaves the door open for the mystical or ineffable. A lot of the history of science is about finding things that used to be considered unknowable or unexplainable and actually figuring out how to explain them.
Right. I mean, that's been a whole iterative process, especially in astronomy. I mean, that the whole geocentric model, it's like, well, we have these things that we really aren't supposed to question because maybe it's just not for us to know in a philosophical sense, but really we can use our methods to do so and explore that.
Yeah. And I guess, part of the question is whether or not that will always be true.
Yeah.
Right. I guess I go into it thinking that we should try. Right. I think there are questions that we probably will not know the answer to. And maybe that's a failure of imagination on my part, right? 100 years ago, you would have asked me something about this, and I would have said something that we probably know a lot about these days. But you can think about some questions about the nature of the universe, or the nature of consciousness, or the fundamental neuroscience of morality, or things like really hard questions.
Like a moral substrate that's not really quantifiable.
Right. These hard questions that we think of as, well, maybe we'll never know enough to know. Maybe it's always going to be impractical for us to even to do experiments to try to figure this out, to do this sort of systematic study. Maybe not, right? But I guess as a scientist, I proceed with the hope that we can try, to answer those, and that there really shouldn't be a realm of study that is off limits, that we should say, well, it's not worth it to investigate this, to try to find some sort of systematic way of interrogating this. So yeah, I mean, I think there are still plenty of unexplainable things, plenty of things that we might consider mystical or ineffable or very personal in nature. And I'd like to think that we could someday try to learn more about them.
Explain it all, maybe. Yeah. So the reason I ask is because the trend you mentioned is, well, 100 years ago, there might have been questions where like, oh, there's no way that's answerable, and now it is. Or, a couple hundred years ago, the idea of controlling electricity would have been essentially magic, like the idea that we have the technology we do, and that's certainly the trend of technology. But at the heart of quantum mechanics, we have this Heisenberg uncertainty principle. And my thoughts on this is that that's sort of an epistemological problem, because to me, what it seems to be imposing is a lower limit on what we can know in relation to two constants. So if I could get you to explain incompatible observables, like,
sure.
So and the Heisenberg uncertainty principle more generally, I'm sure most people are familiar that, well, there's some quantities that can't be measured together, or that measuring one means we can't quite measure the other. But to me, that seems deeply epistemological. What do you think about that?
Well, yeah, that's a really good point. That so quantum mechanics, as you said, there are some theoretical limits that are placed on our ability to simultaneously know or extract information about two quantities or two sets of quantities from a quantum system. So the one that we most often think about is position and momentum, right? And there are a whole lot of jokes and memes about that. But the fundamental idea is that the better you understand a particle or a system's motion, the less well you actually know precisely where it is. A way of thinking about that that might make a little bit more sense is if we think about something like a wave, okay? Just a sine wave. If it is an infinitely long sine wave, infinite in duration, then we can measure its frequency or its wavelength as precisely as we possibly can, right? And we can say, yes, this wave, this infinite in extent wave, has this one unique wavelength, right? If we only have a portion of a sine wave, just a couple of cycles of that sine wave, and then the rest of it is just kind of flatline, then for that portion, we could say, oh, well, yeah, that looks like a wave with a particular frequency. But because it shuts off after a certain amount of time, that actually places a limit on our understanding of what that wavelength really is.
I have a quick clarification.
Yeah,
when you say shut off, do you mean it continuously tapers off and reduces in amplitude, or is it just like a solid edge?
Doesn't actually matter. It could be something where you've got a flat line, and then you've got a sine wave for a couple cycles, and then it flatlines again.
I'm sure you know why I asked this question to Wells.
Or it could be something like you have something that ramps up to a full sine wave and then kind of gradually decays away. In either case, if you think about, well, what is the frequency content of that wave? Well, it can't be just a single unique frequency, because a single unique frequency is something that represents this infinite in extent wave. So what we really think of it is, what if we had a sort of central frequency? Most of the wave is this frequency, but if we combine it with waves at other frequencies in just the right way, we can actually get the shape of the wave that we want. Right? This is the process of doing what we call Fourier analysis or Fourier decomposition. So we can imagine taking a collection of waves at different frequencies and adding them together in just the right relative phases so that we end up getting this picture of something that starts and then stops later on. And that always results in some sort of range of frequencies. And it turns out that that range of frequencies is wider if the size of the oscillation, if the number of oscillations that you get is smaller.
I see.
Right. So if you think of this wave as being just a short blip or a pulse instead of this really long wave train, the shorter the pulse, the more frequencies, the wider range of frequencies we need to kind of add together to cancel out all the other stuff and just leave that little pulse. And that is sort of the mathematical underpinning of what we think of as the Heisenberg uncertainty principle. In this case, it's the idea of the spatial extent or the time extent of that wave and its frequency content, right?
So do you see this arising as a result of the mathematical system we use to describe nature, or do you see it as a quite fundamental nature is sort of obscuring our ability to measure it?
Well, I sort of think of it as both, right? I
That's
mean,
fair.
when we first think about the Heisenberg uncertainty principle and understanding it, it really is proving it as a mathematical theorem, and it really is relying on this interplay between what we think of as these reciprocal quantities. So whether it's the time extent and the frequency, or whether it's position and momentum,
Right.
these are reciprocal quantities to each other, and it's not just any two physical quantities that are related in this way. It definitely has to be these sort of conjugate pair quantities. But it's really, there's this, a mathematical understanding, this Fourier sort of approach to understanding the underlying uncertainty there. But yeah, I mean, it definitely does have real world implications for our understanding of a quantum system, and it's something that has caused quite a lot of philosophical disagreement and conflict in our interpretation. So the famous quote from Einstein that God does not play dice with the universe, right? And the search for perhaps an understanding that would include a sort of strict determinism and a sort of an underlying perfect knowledge that maybe is inaccessible to us, was sort of for many years sort of what was thought of as the best way of understanding what's really going on in quantum mechanics. Like you said, that somehow someone might be able, some godlike entity might be able to know everything there is about this quantum system, but we mere mortals with our primitive equipment can't. And maybe we could figure it out later on. We could come up with some better theory that helps us to understand the world. And the work of John Bell and the Bell inequality of Bell's theorem really showed that interpretation of quantum mechanics was flawed. That there really isn't a wizard behind the curtain. That if we're just clever enough, we can rip away the curtain and see behind it. That there's no more there than what is sort of embedded in the quantum state, and that really does lead to these fundamental uncertainties in understanding the system.
But we do get this sort of confusion where quantum mechanics broadly is just used as like a rug sweep for things we don't understand. It's like Marvel does it all the time. It's like, oh, technology we don't get, that goes under the quantum rug, and it's sort of left there. But that's not your view.
No.
Okay, I see. Well, thanks so much for talking today. If I could have you, as per tradition, sign the sheet, and then
I'd
we
love
can
to.
get finished up. That'll go on a board in my room somewhere.
Okay.
So awesome. Well, Dr. Wiegert, thanks so much for talking today.
Thanks,
Appreciate
Will.
it.